All right, so let's get started talking about learning something about software engineering and programming and that sort of thing. We're not going to cover a lot of Java in this particular lecture, but we'll cover some general concepts about computers and programming and sort of a little bit of the background that you need to know to move into learning a programming language like Java. So really what we're going to do is talk about the history of computing systems a little bit. We're going to talk about how computers work in terms of switches. We'll understand how code is actually translated from the programming language that you write, the text that you write, to the machine code, the ones and zeros that the computer understands. We'll learn a little bit about how Java does that conversion and talk a little bit about computer languages and some things like that. So just programs in general. You know, if you're going to be a software engineer, you have to know something about how the computer works. You know, it's like it's helpful if you're say a race car driver that you understand something about how the engine works and changing gears and you know what can go wrong and the best time to change gears. You need to know what RPM is and all that, right? So it's very similar with computers, software engineering and computer science, that sort of thing. You need to understand how the computer works, or your code can be pretty clunky and not work very well when you write programs. So computers basically function by manipulating bits, BITS, and that stands for binary digits. Computers are made of billions of switches, and these switches are combined in various configurations to do various functions, like carry out a logical operation, like an if statement or so on. You know, if this is true, then do this. So these switches form really complex circuitry, and we'll cover some of that later on in the program. But for now, um, each circuit, you can think of each single circuit as a circuit that has power on it or has no power on it, a circuit that's complete or not. And in actuality, the circuit either has high voltage or low voltage, okay? If it's high voltage, it's a 1. If it's low voltage, it's 0. But just for explanatory purposes, suppose we have a light switch, okay? And we want to indicate a 1. We would turn the switch on, the light would come on, and that would be a 1. If we turn the switch off, then the light goes off, and that would be a 0. Okay, so that's the idea. Now, I'd like to direct your attention down here to, or over here to this participation activity right here. So your book chapter, your Xi book, has some reading to do, and interspersed in that reading in each chapter are participation activities and challenge activities. So there are two kinds of assignments in your course. There's the reading participation assignment, and then there are lab assignments. And there may be other things, you know, could be the occasional quiz, could be tests or whatever. But basically, there's that reading participation assignment and lab assignment. So what I'd like for you to do is as you watch this lecture on one screen, either on your phone or um, it's nice if you have a second screen, a second monitor for your computer, and you can work on one of the monitors and play video on the other, that kind of thing, or cut and paste from one monitor to the other. It really speeds your work up. You know, that's really great. Or you can sometimes you can use a TV. If you have a smaller TV, you can use that as a second monitor and just plug it in with HDMI. But you should go through the chapter or go through the lecture and listen to the lecture. And as you listen to the lecture, you should do the reading participation assignment. Okay, so you would go into Moodle, you would click on that reading participation assignment, you would open that up on one screen and watch the lecture on the other, because the way the lectures work, they go through that chapter and then you pause the lecture and you do the participation or reading assignment as you or challenge assignment as you come to it, and so on. So and then you get points for all those. When you're finished with the unit, you've gotten points from your participation reading activities. Okay, and then you do your labs and you get points for that. So it's a really nice way to learn as you go through. So every time you just do one of those activities, and the participation activities generally aren't that difficult. Some of the challenge activities you'll run into are a little bit more involved. And then the labs, by the time you get there after doing all these activities, you should be able to do the labs. So that's the kind of the way this works. Now, I just want to point out the red text down here, okay? So this is really important. And basically what that says is when you go to Moodle, you should click on the assignment links, which will then open up your Zybook. Don't go into the Zybook and then go directly to the assignment and do it. Click on the Moodle link, because clicking on that Moodle link allows the Zybook to send your points back to Moodle and update the gradebook and give you your points. So you want to always go through that assignment link in Moodle. Okay. Okay. Now, binary digits, a bit. It's a binary digit. It's either a 0 or a 1. Binary means, 2. So it's either a 0 or a 1. And computers are made up of lots and lots of circuits containing binary digits. In the 1800s, people began using electricity. They wanted to turn a light on or off. So basically, a switch just allows you to break the circuit, going from the generator all the way through the wire, all the way through the light and into the ground. It lets you break that circuit, okay? And then reconnect the circuit so you can turn the light off or on. You just break the flow of electricity with the switch. In the 1900s, people started creating switches that can be controlled electronically. You have a wire coming in, and if there's power on that wire, that lets power flow through two other wires. It allows a circuit to be completed, okay? And that's how transistors work, and so on. Using electronically controlled switches, you can form circuits a little bit sort of on the fly, and you can do simple calculations. So a positive voltage is a 1, and a 0 voltage or low voltage is a 0, okay? Those zeros and ones are binary digits. When you connect a lot of these switches together into circuits, you can perform calculations like multiplying two numbers, all kinds of things, or you can do logic. As the circuits became more complex, the first electronic computers were developed in the 1930s and 40s, and those consisted of about 10,000 of those electronic switches connected together. In fact, when when computers were first created, one of the very first ones, ENIAC, you'll notice these wires hanging down in the picture. If you've ever seen video or pictures of old telephone boards where the operator would plug in two wires to connect a call, these early programmers are plugging in wires to make circuits in the computer. And actually, that's how it was programmed, by plugging in those wires. Early computers were big. They took up entire rooms. Well, they still are large sometimes. They can take up entire rooms, but they do a whole lot more. So early computers took up entire rooms. They performed thousands of calculations per second, whereas now we can do billions. Um, and one of the early uses was actually tables of ballistic trajectories for artillery officers. So when an artillery officer is out there, they have to figure out, for a certain amount of powder in the gun and a certain weight of shell, I want this shell to go, a certain number of yards. How high do I have to elevate the barrel? And so they had these tables that they would look that stuff up on. And in those tables, initially, it took a long time to create those because they were created by rooms full of people doing calculations. Well, you can do all of those calculations a whole lot faster on one of these early electronic computers. So that was really a motivating factor for some of these early machines to do those kinds of tables and produce those tables, the same calculations over and over again with different numbers. So they create these groups of circuits and called processors that process or execute this list of calculations, this list of instructions. And sometimes the instructions, like an ENIAC, were created by plugging in the wires, as I mentioned. Today, processors fit on a chip about the size of a postage stamp and can contain millions or billions of switches. These are electronic switches over here on the right, various types of them. The far left one here is a relay. It's a mechanical switch. I believe that's a relay in any case. So you put power on a magnet. You make an electromagnet, pull in a bar, and when that bar comes in, it creates a circuit. This is a vacuum tube, which the British refer to as valves, because they let current flow if you put power in on one certain one of these inputs. This is a transistor from, say, around the 1970s, and you'll notice there are 3 wires. So if you put power on one of the wires, that allows the circuit to be completed across the other 2 wires. So it's a switch. Power on, that lets power flow through these other wires. And then this is an integrated circuit on a chip over here on the right. The quarter there is so you can see how big these things are. So that's basically the size. And there could be millions of transistors printed on this, or billions printed on that chip. So instructions are stored in memory. Data is stored in memory. A memory circuit is a circuit that can hold its value. It's either going to be 0 or it's going to be 1, and it's going to stay that way until you change it. And we can talk about how that's done in another class in this series. But basically, these memory locations in your computer in the random access memory have addresses. They're like a series of mailboxes that have an address, and each of those stores zeros and ones. It stores some value. A computer is a processor that interacts with the memory. So it loads up some data from the memory and does some kind of executes some instructions on that data, and then it puts the results back into memory. Okay, so this is just an example. If you look at the chart, of something called assembly language, you don't have to learn these instructions or anything. It's just to give you an idea of how the chip works. So the chip understands things like add and subtract and multiply and divide, or jump to a different instruction. That's the kind of thing that a processor understands. And so it understands that in terms of commands that are listed as zeros and ones. So add X, like this first command, actually would be converted into ones and zeros and passed into the processor, and the processor would execute that command. So that's called assembly language. It's a very low-level language. In this slide, you can see on the right those assembly language instructions right here. And then on the left, you can see how they're actually converted into opcodes, or commands for the chip. And so this assembly language is converted into these opcodes, and that's placed in memory, and that's what the computer actually executes. It starts at memory location 0, or whichever memory location it happened to be stored at. Starts at that memory location, the first one, and does that instruction, and does the next instruction, and the next instruction, and the next instruction, and so on. This is another Zybook participation activity. So you should go and do this activity in the Zybook as we move through here. I'm not going to explicitly mention these anymore. You're just expected to read through as I go through it in the lecture and do the participation activities as you get to them. So with the first computers, programmers were forced to write the instructions, literally write out all the zeros and ones. And, that's hard. It's hard to to read and understand once it's written. It's hard to debug. It's easy to make a lot of mistakes. So those are called machine instructions. And those machine instructions, a list of those is a program, an executable program. We call it machine code or sometimes object code. Because the zeros and ones are difficult, we wrote programs called assemblers. And they take some sort of assembly language, those assembly language instructions, which we mentioned earlier, like add or multiply, and they convert those for us into that object code. And assembly language is easier to understand, but it's still very low level. It can only add numbers, multiply numbers, jump to a certain location, that sort of thing. So it's hard to write structured programs. It's hard to read those programs and understand what they're doing in any certain place. So later on in the 60s and 70s, programmers started creating high-level language, and actually even in the 50s. Um, so some of the first ones were languages like COBOL and Fortran and ALGOL. So COBOL, for example, stands for Common Business Oriented Language, and it was a sort of a language that had lots of words, so business people could write out words that they understood and get it to do things. Fortran was used by engineers. It was formula translation, so you could take a formula like this one and actually convert that, write that formula so that a computer would execute the formula directly, and you didn't have to write all that machine code like add and multiply and divide. You could just write it like a regular formula. Another language was called ALGOL, for algorithmic language. Um, and so these high-level languages, programmers wrote compilers. So you would write out your code in text, and then the compiler program converts that code into those ones and zeros, into those executable programs. So just in general, machine instructions are instructions to a computer represented by zeros and ones. They're binary instructions. An executable program is a sequence of instructions together. It's starting with the first one, going to the second one, third one. Programs are sequences of instructions. And compilers are programs that convert written high-level languages into machine instructions. This is what a high-level program might look like. Put hourly wage. So that would print out the phrase hourly wage. In computer software engineering, computer science, we refer to this inside the quote marks as a string because it's a string of characters. So that would output the string at enter wage. I'm sorry, it said hourly wage. It would output the string enter wage. Then this next instruction would get whatever the user types in and store that wage into this variable, hourly wage. And then this line would then output to the screen, salary is, followed by the calculation of the salary. Okay, so here's the output right down here. You can see it. It says enter wage. The person types in 20. It says salary is, whatever the salary was, 41,600. So the programmer, that's going to be you, will type this higher level code, and then the compiler will convert that code into these ones and zeros for you, which you rarely, if ever, look at. And that's the code that's actually executed by the CPU, by the processor, by the computer processor. You'll notice this is some kind of a text file. It'll have some sort of a file extension on it. It may be .c for C programming language. It may be, something else for Java, .java for Java. And then when it's converted in Windows, for example, it'll have a .exe on the end of it. And you can set your Windows so that you can see those file extensions, and I kind of suggest you do that. So if using the above approach, that approach, whenever you wrote a computer program, say I write a computer program for a Mac. If I write that program for a Mac and it's compiled for a Mac, it can only run on a Mac. And if I want to write that program for a different computer, I have to rewrite it for a different computer and then compile it. Java, the language we're going to look at here, is an attempt to get around that. An attempt to so that you only have to write the code one time and it'll run on any system. And the way that works is each computer that you have out there, each type of computer, what we're going to do is write a Java virtual machine for that computer. So that Java virtual machine will run is written specifically for a Mac. Another Java virtual machine is written specifically for Windows, okay? And that Java virtual machine understands the Java program that we write, okay? So we write one Java program, and then it'll run on any machine because the Java virtual machine on that computer understands bytecode and understands how to convert that bytecode into the machine instructions for that particular computer. So now we have this system where we can write a program once and it runs anywhere. And that was really the initial purpose of Java. Java is very popular now too out in the world. It runs a lot of things in the back end of various programs and so forth. Now that means that the program execution is a little bit slower, but the executables are portable. You can move them around to any computer. All right. Let's look at what the various devices and parts of a computer, a little bit of the architecture or organization of a computer. So computers have input or output devices. They have screens, monitors, keyboards. They also may have microphones, speakers, printers, USB devices, I/O devices like that. We commonly call those computer peripherals because they're around the periphery of the computer and they're connected to it somehow. For storage, a computer might have, and when I say storage, I mean long-term storage. There's memory inside your computer, which we call RAM, random access memory, because you can address it by address, each byte by address. But there's also what's called secondary storage. So the RAM memory in your computer can go away when you turn the power off. But the secondary storage, where your programs are stored and important data and all of your files, that's stored in secondary storage, and it doesn't go away when you turn off the power. You turn the power back on, and then you can load it up again and keep working on your Word file or whatever. A common device for secondary storage now is a solid state drive or SSD. Old hard drives use spinning magnetic disks to store data, and the newer drives, SSDs, are non-volatile memory, so they just don't go away when the power goes off. Computers also usually have a screen or a monitor, so you can display things on the screen, a keyboard for input, that solid state drive, random access memory, as I mentioned. Some other important things, I've mentioned addressing and memory. So we basically, if you looked inside these chips in the computer, what you would see is billions of individual circuits that store one bit. Well, what we do is we kind of arbitrarily divide those bits into 8 bytes, 8-bit bytes. And each of those bytes we address, we give it a memory address. So byte 0, byte 1, byte 2, byte 3, and that way we can identify places in the memory and we can go get data and so forth. And then processors, originally the processors were 8-bit processors. Now we do them 64-bit processors and move 64 bits at a time. But that's the idea. Basically the smallest unit that you can address individually is an 8-bit byte. Okay. And then the processor, or CPU, Central Processing Unit, runs the computer programs. It reads and executes instructions from the memory, writes data to the memory, that sort of thing. The system, your computer, when you turn it on, it automatically boots up some programs and starts them running. And those programs are called the operating system. So the Windows operating system might be on a computer, and when you turn the computer on, the basic input and output system is red, and it starts loading up the Windows operating system. And once Windows is loaded up, you can start interacting with it. And Windows, the operating systems today are very complex computer programs. There are more than one program. They're all running together, allowing you to do all these different things. And we'll study operating systems a little bit. And then another kind of memory is the cache memory. So in addition to the random access memory that you go out, that the central processing unit goes out and reads and writes to, there's also cache memory. Cache memory is much faster. It's very close to the processor, and we store things in the cache that we're going to use over and over again, and that makes your computer faster. All of these devices, all of these devices are connected and controlled by a clock. So the processor can write to the system bus. It can write to the wire connecting to the memory. It can only do that on certain clock cycles. On other clock cycles, it has to read, because you can't have one device writing at the same time another device is writing to something. You know, you have to, everything is in concert. It's like a big dance, and it's governed by that clock. So again, memory, random access memory. Random access memory temporarily holds data while the computer's turned on. It's much faster than an SSD drive or a hard drive. It's called random access because you can access any byte in memory by its address. You don't have to read the memory from byte 0 to byte 2 to byte 3 to byte 4 to get byte 4. You can just say, give me byte 4. So that's why it's named random access. You know, a lot of data used to be stored on tapes. If you've ever seen old movies, and they had these big wheels of tape, and you'd have to read that tape, you kind of had to go from the beginning of the tape to whatever it was that you wanted and read that. Or maybe you could back up some arbitrary amount and then start reading forward again until you got to what you wanted. There was no way to go really to a specific place on the tape. The processor runs the programs. It reads and executes instructions from memory. And in fact, it does that in a loop over and over and over again. You know, read, decode, execute, read, decode, execute. That's what it does. When the processor's turned on, it starts executing the program in the BIOS, the basic input output system, which allows it to load the operating system and so forth. And so then it begins to execute the operating system, and that allows the user to run other programs and connect to peripherals and so on and so forth. Processors are called CPUs, central processing units, or sometimes microprocessors, things like that. And then because speed is really important, the processor may have a small amount of random access memory on the chip called cache memory. Okay, and that cache memory is accessible much, much faster than the RAM, but it's also a lot more expensive. So that's why everything isn't just made out of that kind of memory. And then the clock. So the processor's instructions execute at a rate that's governed by the clock, which ticks at a specific frequency. So if you had a 1 megahertz clock for a really cheap processor, like one in a microwave oven or washing machine or one of the first computers that I used, it ticks about 1,000,000 times a second. So it could do kind of 1,000,000 instructions a second. A gigahertz processor, 1 gigahertz processor, ticks at 1,000,000,000 ticks per second. And those kinds of processors are in mobile phones and some desktop computers. And so you can do billions of instructions per second, and that's what's going on in the computer in front of you. It's executing billions of instructions a second. It's trying to mine, for example, I'm talking. It's breaking my voice up into binary chunks and storing my voice coming in, and it's showing the slide on the screen. It's doing all of these things really, really fast. So I can't tell that it's switching back and forth between these different processes, actually. So here's the sort of general organization of these components. And if you take a look, you'll see that here's the processor, the central processing unit, and the cache memory. We got a screen here to look at and a keyboard. This is connected to the main memory, and then that's connected to the secondary storage where all the documents and programs and things are stored. How did all this evolve? Well, computer engineers, we had those old switches and they were plugging in wires to program computers and things. And then they switched to vacuum tubes, but vacuum tubes burn out a lot and they're kind of big and they get hot and they take a lot of power. So engineers created smaller switches called transistors. And those transistors allowed you to make things much smaller. Transistor radios came out, and you could put one of those in your pocket as opposed to having to carry it around in a case. And then in about 1958, the first transistors were put onto a single chip. They were integrated onto the chip, so you didn't have to have wires connecting the transistors, and that made things really small. So Moore came along. He's was the CEO, became the CEO of Intel, and those by 1971, Intel produced the first integrated chip IC called the 4004, which had 2,300 transistors on it. Okay. By 2012, a single integrated circuit had several billion transistors containing multiple processors, and each processor is called a core. So multiple cores on a chip. Just a little bit of advice before we end. If your computer is going slow and you don't know what to do to speed it up, rather than go buy a new computer because my old computer is just quote junk, most of the time, the problem is that programs have gotten larger as you've owned your computer over the years and more complex. And a faster CPU won't help that much. But what will help it is more random access memory, more memory. And you can very often add memory to your computer and make it faster. So if a computer's slow, it's getting a little bit older, and you want to jazz it up, and you don't want to spend all that money on a new computer, a way to do that is to add more RAM, random access memory. And it's not hard to do. You can watch a video, you can do it yourself. Okay. Moore's law says that random access memory and chips and so forth, um, double in size every couple of years, and that's worked up till now. Now, yeah, not necessarily. So now what we're doing is adding more CPUs rather than just buying faster CPUs. Let's talk a little bit about language. So we write computer code in high-level languages, and some of them are notable. So in 1978, just from a historical perspective, Kernighan and Ritchie wrote the C language. They were working at Dennis Ritchie's at AT&T Bell Labs, and they used computers for automatic telephone call routing. And they wanted to write, they actually wanted to write a high-level operating system called Unix, but there wasn't a language that was structured enough to write Unix. So they wrote the C language and then the Unix operating system. And Unix is still out there in the form of Linux, which is an open source form of Unix that runs much of the world behind the scenes. You don't see it quite as much on desktop computers, but the databases that you're connecting to in the world and the web pages that are being served up, many of those are being run on the Unix or Linux operating system. In 1985, C was kind of converted into an object-oriented language to support object-oriented programming, and that's called C++. And then in 91, engineers at Sun Microsystems, which is now owned by Oracle, developed the Java language. And the idea was that it would be portable for different processors, and Java is heavily used out in the world. The TIOBE Programming Community Index indicates the popularity of programming languages. Now, that doesn't mean which one is best, and it doesn't mean which one really is used the most in the world. It's the one that right now is most popular that people are diving into, I guess you might say. And right now, this is the list of language popularity that people are doing. So Python is first. Python is very popular for artificial intelligence, and you will learn Python in this program. That's the reason Python's at the top right now. It's because so much is being done with artificial intelligence. Why don't we teach Python to begin with? Well, Python is, it's hard to explain why we don't. The reason we don't, until you know Java, it's hard to explain why we don't teach Python. The reason we don't is Python doesn't have several features that you need to know as a programmer. Also, Python is heavily used in business on the back end. Not Python, I'm sorry, Java is heavily used on the back end. And Java is structured enough and has data typing, so it's a good language to teach you with. It's probably a little less difficult than C and C++. It's a little bit higher level. And so it's a little easier to learn than C and C++. C and C++ are listed there because C and C++ are called by Java libraries to do a lot of things in artificial intelligence. The libraries are already written, but that makes the C and C++ popular. Are more programmers writing in C and C++ right now than they have in the past? Probably. I would say maybe not. I don't know about that. So really, in terms of, I guess, importance right now, I would say Python and Java are at the top, and then followed by C#. JavaScript is used in almost every web page. If you look down here, so JavaScript is used down here is used in web pages all the time. So it's in almost every web page that you click on that does something interesting has JavaScript in it. JavaScript isn't Java, but it's very popular. So the way they rank these, I'm not sure. Also SQL, Standard Query Language, down here at the bottom, which you also will learn. SQL is used in every database in existence. So I'm not quite sure how they judge popularity. I think it's the thing that's growing the most at any particular instant, not necessarily the language that's the most important. So we talked about how computers are put together in a general way. We talked about programming languages in a general way. But we're going to start learning Java, which is an object-oriented programming language in a bit. But what does this all come down to? We've got all of these languages and so forth. You know, the first thing we're going to do is teach you a programming language, and probably when you think of software engineering, you think of being a programmer. Really, you're not. Really, what you're becoming and what we want you to become is a problem solver. And this is a really nice little example of that. Say you're a chef. Well, you could write a recipe in English, or you could write a recipe in French, or you could write a recipe in Chinese. But the core process isn't putting it in the language, isn't really writing it in the language. The really important thing is creating the recipe. The important thing is knowing what goes into the dish and what the dish is going to taste like, and making something new that brings out this new dish, okay? So creating a program is the end step of solving the problem. Programming is about putting into words how to solve a problem. It's creating a methodical solution to a given task, and that's so let's look at a problem, a non-programming problem. Well, really, all problems are programming problems because we could program this in and we could run it on a computer as a simulation or otherwise. Anyway, so let's say we have this person and they don't like matching their socks after they do laundry. There are three kinds of socks. There are gray socks, red socks, and yellow socks, okay? And we want to figure out the best way to match socks. So this person says that a friend comes in who's not a computer person and suggests just putting all the socks in a drawer, and then each morning you take out two socks, and if they match, you have matching socks. If they don't match, you put them back in the drawer and you do it again. Well, the person who doesn't like matching socks says, "No, I don't want to do that. That could take forever." And in fact, that's a terrible algorithm because we don't know how long it would take. I mean, if you're just incredibly, super, horribly unlucky, you might never match your socks. You could keep on trying that and putting them back and trying that and putting them back. And you may never get a pair of socks that match. Of course, we know you would. And we can even say on average how long it might take, but we can't tell you exactly. So that's not a very good recipe for matching socks. It's not a very good algorithm. Okay. Now here's what I want you to do. Pause the video. Pause the video now and think about it. And think about how you can make that a lot better. How could you write out a series of steps to match socks that would be much, much better? So pause the video. Okay, did you think about it? Maybe come up with a better idea? So here's how you can do this. So you pull out the first sock and you pull out the second sock. You don't put them back. You just put them neatly next to each other. Then you pull out another sock and then you put it down. If you have three different kinds of socks, then the fourth sock that you pull out will match one of the first three. It has to. Try it if you don't believe me. Tear four little squares of paper, write a color on each square, red, gray, or yellow. Put them in a pile, take them out one by one. In the worst case, you have to take out four of the squares or four of the socks before one matches, okay? What we say about this is that this problem requires 4 computational steps in the worst case. The computational step, what do you mean computational step? That's just crazy. I'm looking at socks. The computational step is comparing the sock colors, okay? In the worst case, you have to do 4 comparisons. That's a great algorithm. Now I know exactly how long this is going to take in the worst case. Now you're thinking like a software engineer. That's how software engineers think. So what did we cover here? Computers are made of billions of switches combined in circuits to carry out various operations. Computer memory is made of electrical circuit, each single circuit representing one bit or binary digit. Written programs are compiled into executable binary code that the CPU or central processing unit understands, decodes, and executes. Important system components include the screen, keyboard, hard drives, SSD drive, RAM, operating system, CPU or processor, cache memory, clock. There are hundreds of programming languages. Java is one of the most used. And software engineering is this process of solving problems, of finding algorithms, that is lists of steps that solve problems in a finite amount of time, and then implementing those solutions in one or more computer languages, writing one or more programs to implement those algorithms or solutions. Good. Okay, let's move to the next one.